Okay, so geometric optics, mirrors. This stuff is fun. Uh, if you find after a few minutes you're not really enjoying thinking about it, close it up. Don't worry about it. It's not for you today. Maybe open it back up later on. Maybe you'll be more rested one day. Maybe you'll never find it interesting. But it should be fun right here. If you don't have fun thinking about what we're about to start doing, then do something else that's fun. All right. Here's a mirror. You can see here we've got this mirror right along here. Okay. Now, I'm going to treat this as a parabolic mirror. I think it's drawn as a circular mirror. For our purposes right now, we're going to treat them pretty much the same. However, really parabolic mirrors are going to do exactly what we want them to do. And if the mirror is over a small section, a small piece of it, they're not that different. All right, let's circle out. Let's erase all this nonsense. So here you got this mirror, and it starts up here, ends down here. We're probably not going to use those edges anyway. And so what happens is this mirror, right now, it's kind of treated like a sphere. If you could imagine, if we continued this circle, you see here it's at 8. It would loop around to around 16 and come back. Of course, if this is a parabola, it doesn't do that. It never loops around. That instead would go off, you get something like this. All right, but let's look at the circular case for now because it's easier to think about. And when you really have to worry about all the differences between them, you can be stronger in this subject anyway. So if here's your center around 8, there's a point in between the actual face of the mirror and the center there called the focus. Here it is. And the focus is literally halfway. So here, 4, unit 4. What's the unit for? We don't know. 4 units away. So let's clear all this junk out. And that's just giving you a little sense. Now, different mirrors have different focal points. If this mirror were instead, let's say, bigger, you would have a bigger circle, something like this. Well, the center maybe would be over here, and maybe the focal point would be here, F. So it really goes with the size of the mirror, that's all. Bigger mirrors, farther out the focal point. Okay, but what is this focal point? Well, the focal point, or the focus as it's sometimes loosely called, that actually is where light is collected. And what do I mean by that? Well, if we take an object, often what we draw is like an arrow, something like this. There it is. Let's see if I can get this thing straight up and down. Oh, I don't want to move you. I want to move you. Good. Okay, so you take your arrow, put it wherever. I'll put it at the 16th. This arrow, you think of it as like a candle. You put a candle there. You can look at the head of the candle. That's where the flame is. And so you have your flaming candle. Let me write. We're going to erase that blob in a minute just to keep our picture sharp. But basically, that thing gives off light in all directions. And so, make a real skinny line. Let's go with our purple candle. So this thing gives off light this way, and 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 this way. Every direction. This is only 2-dimensional paper here, or screen. So it also comes out of the screen and goes into the screen everywhere, like a big sphere or ball around it just spreads. So the light goes everywhere. So if you're sitting somewhere over here, you'll see it. Over here, you'll see it. Over here, you'll see it. Over here. Wherever you are, you're going to see this thing. But that's not really our concern here. Our concern is, does the light that leaves the candle somehow interact with the mirror in a unique way, in a special way? And the answer is yes. So let's clean up all this junk again. All right, let's clean up all this. We'll leave all those wacky arrows and whatever. Now, there are a few of these arrows that we drew there that are actually very helpful. One of the arrows that's very helpful is the one that leaves the candle and comes parallel to that midline that our focus is sitting on. Move this up a little so we can line it up. Boom, there it is. Good. This line over here is called the central axis. That's just a line of symmetry. And the mirror, which, you know, here it's drawn just as like a cup or a letter C, two-dimensional. Really, it's three-dimensional. It comes out over here and goes into the screen, too. But again, we need to be able to draw this and pick it apart. So if you look at that central axis, this ray that just came in, the one we just drew, switch up the colors so we don't confuse them. Let's see, this one here. This one actually is, let's go with, yeah, why not? Let's go blue. Nope, doesn't want to let me change it. Anyway, this one is parallel to this central axis. Cool. Now, why is that special? Well, check it out. When it comes parallel to that central axis, what it does is, oh, bear with me, here we go, good, good. It actually reflects off. Well, what do you mean it reflects off? Well, this is the same as the law of reflection we just did, actually. This one is just like what we did in our regular reflection notes. It hits there, and there's a normal line. Where's the normal? Right around there. The normal's imaginary. It's perpendicular to the mirror at this location, and the ray comes in, and it has an angle of incidence. Here's the angle of incidence. And it's going to have an angle of reflection over here. That's the exact same thing. So let's get that angle of reflection. Yeah, we'll use the purple again. And the angle of reflection is going to match. So in fact, the angle should be same, and it bounces off of the mirror. I don't want a dashed line. Bounces off of the mirror and leaves at that same angle. And it just so happens that that same angle takes it directly through the focus. Ooh. Now, my drawing's not perfect, but you should see the angles there do look pretty similar. And if we had done it just right, the angles would actually be the same. You know, maybe this guy needs a little adjustment this way. Maybe that's a little better perpendicular. But anyway, those angles would actually be the same. And in that case, you see that the light ray came in. The one we followed here was the parallel one off the tip of the arrow, parallel to the central axis, and it went through the focus. In fact, with a mirror of this sort, any light ray that comes in parallel to the central axis will emerge through the focus. Oh, that's a focal point actually has importance. If light rays come in parallel to the central axis, if you essentially angle this thing so it's aimed right at the light coming toward it, the light gets converged or compressed right into that focal point. Cool. Now, there's another ray we like to follow. This one, let's switch up the color. Let's go blue this time. There's one that goes from the tip, and it goes directly through the focal point until it hits the mirror itself. Let's straighten that out a little bit. Oh, we don't want all that. Straighten that out a little bit. Good. So if it goes directly through the focal point, now you see there's all these arrows over here, whole bunch of them over here, here. One of them is going to follow that blue line. In fact, a bunch of them will actually be close to that. And you get the same game as you had before. It's going to hit the mirror and draw your normal line. And if we draw the normal, it's not that easy to draw right here. See if I can move it around a little bit. Maybe it's kind of like this-ish. Draw your normal line. And you will get your angle of incidence matching your angle of reflection again. And so the line will actually go this time, uniquely enough, it will leave parallel to the central axis. There it is. That's not too bad a drawing. And so this is pretty cool here. Look at what we've done so far. We've had light rays that come in parallel to the axis, will leave through the focus. So that's not a bad thing for us to come over here and write. Let's see. It goes parallel to the central axis, will then go through the focus. And now we also have the blue. If it goes through the focus, it will emerge parallel. Well, that's pretty cool. And in fact, there's a couple other rays that are nice ones, that are important ones worth following. And then this will start to speed up a bit. I know this first bit is a little slow. Sorry about that. But we have another one where there's a light ray that emerges from the tip and hits right here at the central axis. And actually, your normal line is in a sense already drawn, because the normal line is the central axis itself. And so that is, boom, angle of incidence, angle of reflection. It will emerge just like it went in, something kind of like this. Move that guy up ever so, stop it, ever so slightly. This finicky thing. Okay, something like this. And then there's one more ray you could follow. So this one was the center. There's one more ray. There's a radial. Now, in this case, it's a little hard to see it, and you could perfectly survive well without it. But the radial, you really wouldn't mess with it with one this far away. Here, there we go. Brown. Let's use brown. That's basically, if this were somehow in the circle, you would take the shortest path to the circle. That would be a radius of the circle. And that would basically take you through here. And I'll show you this again in a nice little applet that somebody made for this. And since this one is supposed to be a radius, if you remember the radius of a circle, like a bike wheel, the spokes, they actually meet it perpendicular. That one's right on the normal line. And so, of course, it will reflect right on the normal line. We'll come back straight through here. And on the normal line, by the way, that was one of the questions on your homework previously, also from the reflection assignment. But on the normal line is 0 degrees away from the normal, so that's a 0 degree incident ray, 0 degree reflection. Now, there's something cool that happened here. Now, if you notice this, but something pretty cool happened here. And it happened right here. The cool thing that happened was all of the light rays crossed each other at that same point. And that's telling you something. That's telling you that this location, oh no, stay where you are. There we go. That this location right here, the tip of the candle, tip of the arrow, is all the light from it leaves in different directions, but it all seems to collect right back in this location, which means it looked like a candle or an arrowhead over here. Guess what it's going to look like over here? Same thing. Same thing. In fact, check this out. Sticking it up a little. Red. Good. What this would actually look like is the arrowhead would be right down there, and the whole arrow would be right here. Let me straighten out our drawing a little bit. There we go. Good. And it's a little off. All right. Sizing's a little off. This arrow would have an image right there at that point. All right, so let's get serious here. And this was the radial. So there are 4 possible rays you can do to help you figure out what we just figured out, which is this business here. What you should notice about this arrow, number one, it is closer to the mirror. Number two, it is smaller than the original arrow or candle. Number three, it is inverted. Now, one thing you should know is that when it is inverted, we call it real. What does real mean? Real basically means it's projectable. It basically means the light rays actually converge or come together at that point. So if you were to put like a screen here and it didn't block the other rays, or you put your eyeball there, you could actually see that tip of the arrow or tip of the candle. Let me pull that wall off of there. Projectable or converges there. The light actually happens there. Cool. So it's closer, it's smaller, it's inverted, and because it's inverted, we know it's real, which means it's projectable or converges. This is called actually a concave mirror. And another name for a concave is what it looks like, meaning when you're over here and you look at it, you see a cave or an indent. We call that concave. I prefer calling it a converging mirror because the converging actually tells you what it's doing. That's its behavior. It's causing light that comes out from this point and spreads in different directions to then converge back over here at this point. Pretty cool. Now, if you notice here, there are tendencies to this. And in fact, let me jump over to the app and show it to you. Because here we just drew this out. And this is essentially what I want you to do in that homework. If you want to try it, draw it out. Draw the parallel ray and then have it reflect through the focus. Draw the, let's see what we do next. Draw it through the focus and have it emerge parallel. Draw it to the center where the center meets the mirror and have it reflect across with the same angle. And then, of course, have it go to the radial, along a radial, which is a little harder to pick, but it should visually line up where it meets the mirror at a point where it is perpendicular to the mirror and then reflects directly back along itself. So check this out. Here's this app. Let's clear all this business up. Okay, so let me get rid of the image too. It's a cool app. You can go play around with this app if you'd like. So what's happening on this app? The following. Take your object. We had it at around, I think we said somewhere around 16. Our image, boom. Look at that. Looks just like what they came up with. There it was. Come on, it made simple. That wasn't that simple. All I did was switch tabs. All right, let's go back over here. Hopefully it's all still there. Yes, there it is. Look at that. In between 4 and 6, smaller, inverted. You too, we're going to reset every time. Let me clear all this up. We're going to stay over here a little while. So we had this one at about 16. And the image, there it was, in between 4 and 6. So our sketch was a little off compared to this app, but pretty good. Anyway, how's this working? Let me show you one more time. Wherever you put the object, you can run a ray parallel to the central axis, hits the mirror. It's just the law of reflection there, and this is a shortcut. It saves you time with measuring angles and all that. Just remember, the parallel comes in and reflects through the focus. Boom, there it is. There's also a ray that goes through the focus and reflects parallel. There it is. Notice you can see where these two rays cross, and that's down beneath the central axis in between 4 and 6. You can have the central ray, so it goes off right where the central axis hits the mirror. Oh, that crosses there too, and even a radial ray. And notice all 4 of them meet right in between that 4 and 6, and the head now is below the axis, so facing down, there's your image. All right, cool. Now, the thing I'd like you to be able to do is get a sense of, depending on where you put the object, how does the image look? The best place to understand this is really from twice the focal length, but the center of curvature. There it is, 8. So if the focus is at 4, the center's at 8. That's the best place, because watch what happens. The image is the same size, the same distance, just inverted. And of course, that makes sense, because if you go parallel focus, focus parallel, center, center, and radius, radius. Here, the radius straight away till it comes back. All right. Notice this is a little bit off. Don't worry about that for right now. So, there it is. And so, this works out nicely. All right. Now, watch what happens. If you use that center point as kind of your balance point, there's your image. If you move away from the mirror, the thing that moves away from the mirror gets bigger. So, and you'll see what I mean in a moment. If you move your object away from the mirror, it stays the same size, but look what happens. It's like a balancing game around that center. One moves out, the other moves in. You see that? One moves in, the other moves out. Whichever one goes out is actually bigger. Whichever one is in is smaller. Now, as it turns out, the object is what it is. If it's a wax candle, it is what it is. It's not going to change size. So it's the image that changes size to accommodate. But qualitatively, you'll do this quantitatively too, but qualitatively, it's nice to have a sense of this. It moves out. Whichever one moves in is smaller. Whichever one moves out is bigger. It's always the image that's changing, though. So if the object moves out, the image shrinks and moves in. If the object moves in, the image grows and moves out. So knowing the center is like the balance point, it kind of allows you to estimate, put this all together. You could always draw them, but it's nice here. Move out, and there's that balance. It's almost like the two of them together equal two mid-distance and mid-size. All right, now, what happens though if you keep going? So we got the center covered. We got if you move in. We got if you move out. What happens though if you keep moving out? Farther, 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 farther. Let's see if we'll run out of room here. The limitations of this app will run out before the limitations of reality. If we keep going farther, 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 look what's happening. What's happening to the image? It keeps getting closer, 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 closer to the focus. And it's shrinking, shrinking, shrinking down to a point. In fact, if you move the object out to infinity, so to speak, and you're not truly moving it to infinity, but you're moving it far enough that the distance is much greater than the focal length, then the image becomes a dot at the focus. Realistically, do we have anything like this? Yes, we have the sun. The sun is like an object at infinity. So if you hold a parabolic mirror up to the sunlight and you orient it so that its center is lined up, you will get a whole lot of light converging right there at the focus. Let's see if we can drop all these in there. There's some issues with the app. But anyway, a whole lot of light focuses at the focus, and if you put your eyeball there, you'll blind yourself. This is one of those, don't ever point a telescope at the sun, unless you have a special solar filter, but you probably don't. So the farther out you go, the closer in the image goes until it shrinks down, 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 down to an extremely bright point at the focus. This is a solar cooker, one type of solar cooker. If you set up a mirror like this and you put food there, it will cook. It will burn. I've literally done it myself. Put a marshmallow there, the thing will light on fire if you got a decent mirror and a sunny day. Easy. Don't put your hand there, you'll get burned. So, this is called the object at infinity. The image shrinks all the way down to the focus, very bright and small, and there. Now, what about if you take the object, I'm going to shrink the object's height a little, bring the object in. Now, check this out. There's your balance point. And now as the object goes in, the image goes out and gets bigger. Can you guess what happens when the object itself gets to the focal point? Oh, go away. Oh, notice once we get to that focal point, you have nothing here. Because when the object is at the focal point, the image is at infinity. The image is at infinity. In fact, if we put these in here, you will see the rays just keep on going. They diverge from each other. They're not crossing each other. And so in that diverging, your image doesn't actually form. So we say the image is at infinity. In reality, there is an object kind of built like this. Let me shrink that one down. There is an object built like this. It's called a headlight. A headlight is like this. You put the bulb here at the focus. You have the parabolic surface of mirrors there behind the headlight. Look in your car next time. You'll see it. And the light then emerges really straight out. You know, this drawing here is only showing some of the reflections. If you could draw the rest of them in here, primarily the light heads straight ahead. And your image will be out at infinity, and you're just going to get a beam of light. You're not going to get a clear image. So once you go inside the focus, things get a little crazy. The image is still there, so outside, remember, balance point was twice the focus, the center. You go out, the image shrinks and goes in toward the focus. You go in, the image grows and moves out to infinity. What if you go inside the focus? Oh, what? So, hold on, check this out now. So the object right now, the image is off at infinity somewhere, which means it just hasn't formed. And then if you keep going in, boom! What is that over there on the left side of the screen? Suddenly, our image has appeared on the other side of the mirror? How could that be? That seems crazy. And it kind of is, but let me give you an example. You can go and live this. And so how does this happen? Well, parallel ray. The ray goes parallel, and it does bounce through the focus, just like you see here. And then there's focus, parallel. You see this little, it's a little hard to judge here, but basically an extension of the focus. If you imagine that orange, back it up, it's as if it came from the focus. And so that one would have continued on past the tip and emerged parallel. The central ray and the radial ray. So let's put these two aside. Let's look at these two just right now. And if you notice, they do appear to cross over here on the back side of the mirror. Now, is there any light back here behind the mirror? Answer, no. The light doesn't go through the mirror and come out on the other side. But the interesting thing is, if you put your eyeball over here, I wish I could draw on this. If you put your eyeball over here on the right side of the mirror, your eyeball would catch a piece of that orange and that red. And your eyeball would say, oh, look, I can tell by the angle of the light where the source is. And your brain constructs an image, and it backs up to where the source must be. And your brain imagines that the image is over here behind the mirror. This is what we call, in fact, we should just come over here and draw this in. Oh, you didn't make me redo it. Fantastic. This is this scenario. So let's go down over here and do this one. If we put our little arrow in over here, let's make them red like we did before. Let's say this thing is here. All right. So what happens? You have parallel focus. Let's do this real quick. Why not? So this thing goes parallel. Ugh. And then reflects back through the focus. Good. And then we got another one. It goes focus, parallel. Now, it doesn't actually start at the focus. It actually starts up here at the head of the light, the head of the candle. However, this is showing you the way it would go. It's hard to see past your finger and do this at the same time. Good. So the light doesn't actually start down here, but you can imagine this is the path it would take. You can actually shrink it up because it's actually here. But that one will emerge parallel. And we won't worry about the center and the rest of that for right now. Basically, what this means is the following. Put your eyeball over here. If your eyeball were over here, and your eyeball caught these rays, here's a big eyeball. So your eyeball's going to be a little bigger here. And there are many more rays than this. It's not like you have to catch those two in particular. You see others. If your eyeball sees these, make it even bigger. Come on, big eyeball. There we go. Your eyeball sees these, the light rays come in, and right here hits your retina, Then your brain says, oh, look at the angle of this light ray, look at the angle of this light ray. I can backtrack based on life experience to where this thing's coming from. And it backtracks to a point. It backtracks to here. Right here. And so it's pretty cool that your brain actually will form an image of this arrow, and the image of this arrow will appear right about there. Pretty cool, huh? That your brain actually can do all that. And it does. In fact, whenever you see anything, your brain is taking the light rays and they're coming together, going apart, it's doing a backtrack and saying, that's where the thing must be. Everything you're looking at, look around the room, everything you're looking at, it's judging by the angles of how the light and the colors and the shading and everything is hitting you and saying, that's where the TV is, that's where the remote is, that's where the pillow is, that's where my sister is, all the same stuff. So here, it actually forms on the opposite side of the mirror. Now you notice, here's the thing. Now this, there is no light over here. There's no actual light here. There's no light on this side. It's a mirror. The light bounces off of it. Nothing actually got behind it. But it looks like it does. And because of that, whenever you have an upright image, this is also called virtual, which means there's no actual light converging there. And so this is a pretty cool thing. You can literally do this in real life. Take a spoon. Let's go back to that. Take a spoon. Nice shiny spoon. Get a big spoon. Not the one with slots in it. A nice big spoon. Take a spoon and hold it in front of you. Now move around. You might have to bring it pretty close to your eyes and nose. Move it around till you can see yourself. When you get close to it, you'll see. Your nose starts to look about like a nose. And when you're far away, your image looks small and you will look flipped upside down. A spoon is a fantastic teacher of this whole mirror reflection. So you'll look upside down and you'll look smaller, but as you get closer, you'll stay upside down and it'll get bigger, 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 bigger. But there comes a point where you start to lose what you're looking at. It starts to just get like blurry and big. And that's when you get close to the focal point. In fact, when you get real close to the focal point, and a spoon is not a perfect parabola, so depending on which piece of the spoon you look in, this varies. But as you get closer to that focal point, your parts will look exceedingly big until, once you actually get to that focal point, you'll see nothing distinct. You'll see light, you'll see color that reflects your skin, but you will not see a clear image at all. There's no focus at all. And then keep going. It's a little hard. You're getting real close to the spoon. But keep going, and suddenly your face will appear, or your nose, right side up and bigger until you get right up on the mirror. And when you get right up on the mirror or the spoon, at that point you're so close that that little piece of the mirror looks like a flat mirror, looks like a plane mirror. And you actually should be the same size, just like you are in the bathroom mirror. Now, the cool thing is, What if you put the spoon, what if you go on the other side of this? Can you do that? Of course. Turn the spoon around. When you turn the spoon around, let's go back over here. We're not going to get too fancy. We don't need to save right now. We're not going to get too fancy with it. But when you turn the spoon around, when you put the object over here, you can still follow those parallel focus and that stuff. That still works with it. Mess around. I'll send you a link to the app. But you'll find that this now is a convex mirror. Convex, so it's curved away from you. And again, I prefer the behavior. They call this a diverging mirror, which I'll show you in just a moment. But what you'll find here is that the image is now upright. It's small. You know, as you move away, it shrinks, but it's upright. You'll be right side up. You won't be upside down anymore. And notice it's on the other side of the mirror. And there's no actual light there, so that must be virtual and upright. And your brain does a little trick saying, oh, I know how it got there. You just back up. And basically, you still can do your parallel focus, except here's how it works. The light ray comes in parallel to the central axis, and it's just law of reflection. It does bounce off as an extension of the focal point. And you can aim toward the focus, and it'll just bounce off as an extension. Let me get a little closer, make this easier for you to see. Come here, object. Oh, he wants to give me love over here. Come on, object. Well, it is what it is. So, you can do the central ray too, and even the radial ray if you want. But you notice they all cross at that little baby arrow in there. And so basically, your brain, your eyeball is on this left side. As the light rays hit your retina and they're diverging, they're moving apart from each other, your retina will run this backwards in your brain and say, aha, there's the image. That's where the light is. The light's not actually there. That's just your brain telling you it's there. So that's enough. That should give you a rough sort of feel. Remember that center is a balance point, and when your arrow is on the concave or converging side of the mirror, when your object is there, you'll actually get real images that are upside down, and that center of curvature is a nice balance point. Same size, same location from the mirror, flipped. And then as you move in, it moves out and grows. As you move out, it moves in and shrinks. When you go out to infinity, it all goes to the focal point. When you go to the focus, it goes out to infinity. So basically, between the focus and infinity, a converging mirror is a pretty well-behaved object. Once you go inside the focus, it gets a little crazy. Your brain does a little trick with the diverging rays and sees the image as upright and virtual on the back side of the mirror. Try it with a spoon. When you flip the spoon around, now you are on the convex or diverging side of the mirror. You can, of course, see here that the red, the blue, the orange, the purple on the left side here are all moving apart from each other. They're diverging. And here you will only get a virtual image upright. And you can still follow those same rules. Parallel focus, focus parallel, central central, and radius radius. And on this side, you know, you're really just going to, as closer you are, the bigger the image. The farther you are, the smaller the image. And you see it's coming closer and closer to that focal point. Okay, go try this with a spoon. It's fun. Hopefully, it ended up a little longer than intended, but hopefully this gives you an idea. Try to feel your way through the problems in the homework.